My name is Rolf Jeltsch from ETH in Zurich, Switzerland, so I try to be on time. And the next speaker is Professor Christian Lubich from the University of Tübingen. He is a numerical analyst from Austria. He studied in Innsbruck, his basic math education, and the thesis, I think, was written in Heidelberg, but then the exam again was in Innsbruck. He started work in numerical analysis first of ordinary differential equation, Volterra equation, and many other things. And he definitely became very famous also to the book on geometric numerical integration, written with his mentor, Ernst Heyer and Gerhard Wanner. He received the Siam-Dahlquist Prize, and now he has extended, in the last many years, he has extended also his work to partial differential equation, and he will talk on the importance of the geometry for structure-preserving algorithm. Professor Lubich.
Thank you, Rolf, for the kind introduction. Well, I'm well aware that my title is not very specific. Dynamics, numerical analysis, and some geometry. So let me go to the ingredients. Well, dynamics, well, that's just about anything that evolves in time. Numerical analysis, well, what I understand by it is the construction and the mathematical analysis of numerical algorithms. And by a numerical algorithm, I mean an algorithm which works with real numbers or their surrogates on a computer, as opposed to, for example, an algorithm that works just with integers. And, well, you can easily imagine that numerical analysis of time-dependent problems is a big area, but how does geometry fit in there? Now, I think it's a commonplace wisdom, which would not be disputed among my colleagues, is that an algorithm that should qualify as a good algorithm is an algorithm that respects the structure of the problem at hand. So structure preservation for a problem that has some structure is a goal that one wants to achieve. But now it turns out that very often this structure is of a geometric nature. Well, physicists might say structure is preserving the structure, preserving the physics of the problem. As a mathematician, one would rather more often say preserving the geometry is what is at stake. So in this talk, the topic is the numerical analysis of time-dependent problems, for which geometric aspects play an important role. And this is a field which has had a vivid activity over the last 30 years and has become known as geometric numerical integration. And mathematicians from very different backgrounds have contributed to this area. And here's just a pile of books related to the subject, just the ones that I had on my office shelves. Some others are leaving, are not here, but I would particularly like to point out the first book, so they are here in chronological order. The first book by Sancerna and Calvo in '94, which was the first book which made this idea of structure preservation for an important class of problems known to a wider audience. And many books, and of course many more papers have followed ever since. And what are the basic questions in this area? I would say there are basically two questions that we encounter again and again. The first one is, how can numerical methods be constructed that respect the geometry for a given problem? So this is the construction aspect. But then there's also another aspect, which is equally important. What are the benefits of using a structure-preserving algorithm? And how can these benefits, how do they come about? How can they be explained? And that's more the analysis side of the problem. And in this talk, well, I cannot do this for every problem that you might find and that has some particular structure. I will concentrate mainly on one particular class of problems which have a very rich structure and which are very important in applications throughout all areas of physics, and these are Hamiltonian systems. So it's mainly Hamiltonian systems which I will consider here. And concerning the first question, how to construct numerical methods that respect the geometry that is inherent in Hamiltonian systems. This is a topic that relates, this construction relates to Hamilton-Jacobi theory, which was, the beginnings of the theory were developed in the 1830s by Hamilton and Jacobi. And the construction of numerical methods draws on that. And when it comes to the benefits of such a structure-preserving algorithm for Hamiltonian systems, this will turn out to relate to Hamiltonian perturbation theory, which was a field that was very active throughout all the 20th century, beginning with the fundamental work of Poincaré. Actually, there was earlier work throughout the 19th century, but Poincaré really put the subject to a new footing. And, well, then there was were theories like KEM theory, named after Kolmogorov, Arnold Moser, and many more. So there's a rich mathematical theory and the understanding of the advantages or benefits of structure-preserving algorithms for Hamiltonian systems comes in relation to that theory, as we will see. So here's the outline of my talk. We'll begin with numerical algorithms for Hamiltonian systems of ordinary differential equations. And we'll get to know the basic ideas and techniques there. And then we will come to two important areas where these basic techniques, which I described in the first section, do not apply anymore. These are Hamiltonian systems which are of a highly oscillatory nature and show a dynamics at multiple timescales. And the other even more important area is Hamiltonian partial differential equations. Then I will turn to something which is different in spirit at first sight, which has to do with a low-rank approximation of time-dependent huge matrices or tensors. And then the two worlds will come together again in quantum dynamics, about which I will say a few words at the end. So let's begin with Hamiltonian systems of ordinary differential equations and try to see what are structure-preserving methods and what are their benefits. Now, Hamiltonian systems in its canonical form is given by a Hamilton function, here denoted by capital H, which represents the energy in a physical system. And this Hamilton function depends on positions and momenta, which together form the phase space. So positions are denoted by Q, depending on time t, and positions and momenta are denoted by P, again depending on time t. And we have this set of differential equations for positions and momenta as written here. And we'll come to several important properties of such systems later, but one right from the start. Such systems preserve the energy. So the Hamilton function remains constant along solutions of these differential equations, and that's easy to see. If you differentiate this and insert the differential equations, you find that the time derivative of the Hamiltonian along the numerical solution is 0. So we have energy conservation, which is fundamental in many physical applications. Now, to motivate why it makes sense to consider numerical methods which are adapted to the structure of such systems, let me give you numerical experiments. And I will do numerical experiments with the simplest of all numerical methods, Euler methods. What we're doing here is we choose a step size, h, denoted by small h, a positive step size, and then compute approximations to positions and momenta. So Qn denotes the approximation to the position at times n times h. And this is done in such a way that we replace the difference, the time derivative by a difference quotient. And on the right-hand side, we have to evaluate the gradients or the partial gradients of the Hamiltonian at some point. And here we have different choices. There are two parameters, alpha and beta, which take the values 0 or 1. And if I take alpha and beta equals 0, then I just evaluate the vector field given by these partial gradients of the Hamiltonian, evaluate it at the old known approximation point. And this is just the explicit Euler method, which goes back to Euler in his treatise on analysis in 1768, which is exactly 250 years back from now. So we can celebrate Euler's method now. If I take alpha or beta equal 1, then the new unknown value is inserted here, and this is known as the implicit Euler method, which also goes back to Euler. But I can also take alpha equals 0 and beta equal 1, or vice versa. And then I get methods which are known as symplectic Euler methods nowadays. And although they were not explicitly formulated as numerical methods, they appear in the work of Hamilton and Jacobi around 1840. And now we take these four methods and apply them to a concrete Hamiltonian system. And the one which is somewhat an obvious choice is take the solar system. And here just take the outer solar system, which includes the planets Jupiter, Saturn, Uranus, Neptune, and also Pluto. Well, nowadays, since 2008, Pluto is no longer a planet. My initial data were chosen from a table of 1988. So at that time, Pluto was still a planet, so it's included here. And we apply these different methods. Well, what would we expect? That over a few revolutions, we would have essentially an elliptic motion. And only over longer times there would appear secular effects. Now, if you use the explicit Euler method, what happens is that the planets spiral out. And this certainly is not what you observe in nature. So let's take the implicit Euler method. Now what happens is planets spiral in until finally Jupiter hits the sun and gets ejected. That's also not what we would like to have. And now we take the two symplectic Euler methods, even with a step size that is 10 times as large, so it should behave worse. But it gives a behavior that looks much better according to our expectations. And Well, it's not a coincidence that I chose this particular example, because celestial mechanics was really at the beginnings the initial motivation for the development of Hamiltonian systems long before they pervaded into all of physics. And there's a centuries-old question about the solar system, namely, is the solar system stable? And numerous mathematicians and astronomers have contributed to these questions, and the first serious efforts seem to have been done by Lagrange and Laplace around 1800. Then, of course, the work of Poincaré was motivated by just this question in his treatises on the three-body system, which are nowadays considered as the fundamental cornerstone to the theory of dynamical systems. In the 20th century, it looked as if with KAM theory, one would get a positive answer to this question. But then, in the last 20 years or so, there's now compelling evidence, compelling numerical evidence, that our solar system is not stable in any reasonable sense. And I would like to I have here this quote from Jacques Lascar, who together with his collaborator, essentially clarified the situation, who writes, "Thanks to the numerical experiments of the last 2 decades, we now know that the motion of the planets in the solar system is chaotic." Well, what he does is give compelling numerical evidence that the solar system is not stable. It's not a mathematically rigorous proof, but the evidence is so compelling that any mathematician would be ill-advised to try to prove this now. There's rather a chance that the proofs that numerical computations that he did would, with some extra effort, be put into rigorous bounds. So we finally have a definitive negative answer. But when you do such numerical experiments, there are 2 things that are important. The one thing is you need a big computer, but the other thing is you need a suitable method. And if we go back to the methods that we had here, you shouldn't take the explicit Euler method or the implicit Euler method. Whereas the other 2 methods, the symplectic Euler methods, they look much more promising. And it's not just by looking at such pictures of the trajectories. Let's look at the energy behavior. We know the energies should remain constant. Now, none of these methods that I presented to you preserves the energy exactly, but their behavior is very different. For the explicit Euler method, the energy grows steadily. For the implicit Euler method, it decays. Whereas for the symplectic Euler method, it stays in a narrow band around the original energy value, and there's no drift even over very long times. And these are 200,000 Earth days, but this might be continued over much longer times, and the picture would look similarly there. And also note that these pictures are obtained in a situation where the step size for the symplectic Euler methods is 100 times larger than that of the implicit Euler method. So the question then is, how can you explain such different behavior? If you write down the methods, they look very similar. But here we see in these experiments and in many others that they behave in a fundamentally different way. So how can this be explained? And this is where geometry enters. Well, the basic notion here is symplecticity, and to formulate this, let me first introduce a notation. I take P and Q together as a vector Y. So Y is the vector composed of positions and momenta. And I rewrite the Hamiltonian system in this way with this structural matrix J, which is skewed symmetric, and multiplies the gradient of the Hamiltonian. And by phi t, I denote the time t flow map, which maps an initial value to the solution of our differential equation at time t. And now there's a characteristic property of Hamiltonian differential equations, which is a geometric property, namely the flow of a Hamiltonian system is symplectic. It preserves the bilinear form defined by this matrix J. And if you look at this relation here, if you replace J by the identity, then it would be orthogonality, which would be related to the preservation of lengths. Now with this skew symmetric matrix J, this is related to the preservation of areas. And this has come to be known as symplecticity. And the flow of Hamiltonian differential equations has this property, but it goes also the other way around. If I have a Hamiltonian system for which the flow is symplectic, then locally this differential equation is a Hamiltonian system. So this is really a characteristic property, and we would like to preserve this in a numerical method. And this leads us to symplectic integrators. So recall this condition of symplecticity here. And we now consider a numerical one-step method, say a Runge-Kutta method or something else. And this is just a map which maps the approximation at time t, at the nth time step to the approximation at the next time step. And this is given by a numerical flow map, capital phi with index h. So h is the step size. And such a numerical method is called symplectic if the numerical flow satisfies the same property, same symplecticity property as the exact flow. So this seems reasonable to ask for. But then the first question is, do such symplectic integrators exist? Well, I wouldn't be here if they wouldn't exist. So there's an abundance of such symplectic integrators, and in particular the symplectic Euler methods that I told you before. They are not just called symplectic Euler methods, they are indeed symplectic in this sense. So these were the cases where the parameters alpha and beta were different. And well, it's quite interesting. They appear somehow implicitly in the work of Hamilton and Jacobi, but then that they might be a useful numerical method, this was only realized by de Vogelaar in a preprint in 1956, which never got published. And only 30 years later, in the 1980s, it was realized that symplectic methods would be very desirable to construct. And this came independently from mathematics with Fung Kang in China, and from particle physics by Ruth in the United States in the mid-80s. And from then on, the subject developed quite vividly, gaining momentum. A decisive year was 1988, when independently Lassagne, Sancerna, and Zuris gave a characterization of symplectic Runge-Kutta methods. Well, that was important because the methods that had been, the higher order methods that had been constructed before required higher derivatives of the vector field. And this was considered undesirable and impractical, whereas these methods only make an evaluation of the vector field. And then in the early 1990s, variational integrators were constructed, splitting methods were constructed. So around 1990, that was the time of the gold rush for symplectic integrators, and many methods were constructed there. But now, with these symplectic integrators, we preserve the geometry. But then there still remains the question, how does preserving the geometry lead to improved dynamical behavior as we observed in the numerical examples? And, well, one observes, it has been observed in numerical examples in all kinds of applications that symplectic integrators applied to Hamiltonian systems behave favorably as compared to their non-symplectic counterparts. But how can this be explained? It's not just in geometry. And in fact, as a word of warning that it's not just in geometry, if you use a symplectic integrator with variable step sizes, according to some standard adaptivity procedure, then you do not have these advantages. So they rely on a constant step size or on a slowly varying step size. But still, how can this be explained? And the key concept that is used to explaining this is backward error analysis, which is a well-known concept in numerical analysis and has originally come up in numerical linear algebra in the work of Wilkinson around 1960, where the idea is that by analyzing a numerical algorithm, you do not look at how big the error is, but you ask, is the result that I have computed, can this be interpreted as the exact or almost exact result of a slightly perturbed problem? So suppose you have an algorithm which computes 2 + 2 = 5. Well, the first reaction, of course, is wrong. Next reaction is the error is 1. But you can also take the viewpoint, well, 2 + 2 is not 5, but if you take 2 + 3, which would be a modified problem, then I get the computed solution 5. And that's somehow what's done here. And then now taking this concept to differential equations, we ask for a modified differential equation which reproduces the numerical solution. So the numerical solution would be the exact solution of a modified differential equation. And this can be constructed as an asymptotic series in the step size h. The original, you take a differential equation y dot equal f of y, and then you add extra terms as in the power series of the step size, and you compute several terms and then put 3 dots, which will occupy us later. Well, the 3 dots will occupy us later because these series typically don't converge. These are asymptotic, non-convergent series, even if f is analytic. But looking at these modified differential equations, it's now quite clear how structure preservation comes into play. Because if we take a symplectic integrator, then the modified differential equation is not an arbitrary differential equation. For a symplectic integrator, this modified differential equation is still a Hamiltonian differential equation. So each term in this perturbation series is a Hamiltonian vector field. And such a result was first proved in a different context by Jürgen Moser in 1968 in a local version. And in 1992, Ernst Heyrer gave a global version of this. And this global version is actually important because to make the techniques of Hamiltonian perturbation theory for near integrable for perturbations of integrable systems available, you need such a global version. So, what we are solving when applying a numerical method to a symplectic numerical method to a Hamiltonian system is actually solving a nearby Hamiltonian system. And well, this can be made more rigorous by taking account of these 3 terms. So you have to truncate this series essentially after a number of terms which is inversely proportional to the number to the step size, and then you get exponentially small estimates. So what I've shown here is capital phi sub h is the numerical flow. this phi h tilde is the exact flow of the modified differential equations. And the two do not coincide exactly, but they coincide up to exponentially small terms, exponentially small in 1 over the step size. And the first such result was given by Benettin and Georgil in 1994, and different proofs were given later. And with a different construction, an early proof was outlined, though not given in detail, by Neistat already in 1984. So, and when you have this result, then can immediately explain, for example, why there is energy this almost conservation of energy. Because, well, if you just ignore this exponentially small error, then the numerical method preserves the Hamiltonian of the modified differential equation, which is close to the original one. And this holds over infinite time. Well, it doesn't hold over infinite time, but over exponentially long times because of this result here. So here, for a symplectic integrator, energy is conserved up to the order of the method, which would be order R would be 1 for the Euler methods and would be higher for other symplectic integrators that have been constructed. So the error in the energy remains small over extremely long times, times which are exponentially long in the inverse of the step size. And this follows from this backward error analysis. But it's not just preserving energy. There are much more. Well, let me still come back to this example that we have here. So the result I just gave you explains the picture that I showed you previously. So the symplectic Euler methods do not preserve energy exactly, but there's a small error over extremely long time. But it's not just about preservation of energy. Well, for a general Hamiltonian system, not much more can be said, but there's an important class of integrable and near integrable systems around which the whole subject of Hamiltonian perturbation theory was developed in the 20th century. And for these, you get much stronger results. You know that the error can grow only linearly in time under very weak, very weak non-resonance conditions. Whereas for a general integrator, the error would grow quadratic in time. Near integrable systems have KEM tori, and you can show that these are preserved, again, over exponentially long times. And there are also results which show that they remain, that you obtain exact KEM tori for all times. And this was developed essentially in the second half of the 1990s. And it comes about by combining the backward error analysis that I presented to you with the rich theory of Hamiltonian perturbation theory. If you put these together, you get results like that. So this looks fine. It looks like a closed subject by the year 2000. But that's not the end. Let's again have a look at this backward error analysis. We have this exponentially small error, but there's a constant c in front of it. And the proofs show that the constant is proportional to the inverse of the Lipschitz constant of the Hamiltonian vector field, or if you have an oscillatory system, it's proportional to the inverse of the highest frequency in the system. Which means that this estimate is meaningful only if the product between the step size and the highest frequency in the system is much smaller than 1. It's a small quantity. But now there are many situations where exactly this is not desired. And then the question is, what can be concluded from symplecticity when backward error analysis is no longer available? It doesn't work because h omega is, say, of size 1. And these are interesting situations because when you treat highly oscillatory Hamiltonian systems, you want to have integrators which are on the one hand symplectic, well, why not? But also allow for large step sizes, which go over the oscillations. And this is also crucial maybe even more importantly, it's crucial in Hamiltonian partial differential equations, where this quotient, this product h times omega, is exactly the Courant Friedrich-Leibniz number, the CFL number. And in all computations, this is typically chosen around 1. And the goal is to make this as large as possible, not to make it as small as possible. And then the question is, can you still say something there? And this leads us to the next two sections. Well, I will first give you, tell you about Hamiltonian systems with multiple timescales, then about Hamiltonian partial differential equations. Let me again begin just with an example. So consider a nonlinear oscillator chain. We have a system of mass points, and we take here equal masses, connected by two different types of springs. The one is a soft anharmonic spring, and the other is a very stiff but harmonic spring. And such a system shows behavior on different time scales. And let me show you what is shown here. So on the first picture, well, in all these pictures, the horizontal line is the time axis. And this will, in all the pictures that will follow, the horizontal line will always be the time axis. And on the vertical axis, several quantities related to this oscillator chain demonstrated on different time intervals. On the first very short time interval, that's just the harmonic motion of the stiff springs. On a larger time scale, there's the motion of the soft anharmonic springs, here shown on the background of the harmonic motion of the stiff springs. More interesting is the third one, to the lower left picture on a yet longer time scale. So here we consider the situation where initially only the first spring was excited and the others were at rest. But then there is an exchange, a transfer of energy between the stiff springs. And this takes place on a larger time scale. And what I've shown you here is the three curves which go up and down are the energies, the harmonic energies corresponding to the stiff springs. And what's interesting here, if you add them up, they remain only almost constant. It's a line which is almost constant, but shows some oscillations. Whereas the line above would be the total energy, the constant line. And if you go over extremely long, over much longer time scales, this almost constant line is still preserved. There's still small oscillations around the constant value, although there are wild oscillations in the harmonic energies, but their sum remains almost constant. And of course, the total energy is conserved in a Hamiltonian system. It's not conserved here in this picture, because this is computed with a numerical method with large step sizes for which the frequency times the step size is on the order of 1. I think it's 2 here. But this is computed with a numerical method which nevertheless preserves this energy. So then the question is again, how can you explain such behavior, which looks very desirable? And let's first look at the continuous problem. So no time discretization as of now. How can you explain this conservation of the total of the harmonic energy? Well, we're not yet here. This is the type of problems that they consider. So we have a harmonic oscillator with one or several, and then later in the PDA case, we will have infinitely many high frequencies, and then this is coupled to a slow but non-harmonic part. And then the time scales that we encounter here, well, we have high frequencies larger than, say, 1 over epsilon, with epsilon small parameter, and then the time scales which correspond to these 4 pictures are epsilon to power 1 on the first scale, epsilon to power 0 on the first picture, epsilon to power minus 1 on the third picture, and in the last picture, this would hold over epsilon to minus n for arbitrary n. Now, how can this be explained? And there are two different approaches for the continuous problem. The more traditional one is to use canonical coordinate transforms, a sequence of canonical coordinate transformations taken from Hamiltonian perturbation theory, which transform the original system to a normal form. And once you have this normal form, typically a Birkhoff normal form, then you can read off the long-time behavior from this normal form. And such a proof for explaining this conservation of the harmonic energy was given by Benetton and Giorgilli in 1989. But this approach turns out to be extremely difficult, and I wouldn't know how to do it, for numerical discretizations. These numerical discretizations do not combine well with these non-linear coordinate transformations, and in particular with sequences of them where I have to control systems. And so Ernst Heyer and I, since 2000, developed an alternative approach, which we called modulated Fourier expansions in time. And the idea here is not to do any nonlinear coordinate transformations, but rather to embed the original system in a formally infinite-dimensional systems, which has nice properties, and then to read off the desired properties from this larger system. And this larger system still has a Hamiltonian or Lagrangian structure with additional invariance properties. And in this way, we get an approach which works both in the continuous and in the discrete case. Now, these modulated Fourier expansions are important in this section, in the next section, so let me show you what the basics of this approach are. This approach has two ingredients. The first one is to make a solution approximation over a short time in the following form. Well, the harmonic oscillator would have a solution which is a linear combination of e to I times the frequency omega times the time t. Now, through the nonlinearity, you can also get multiples of these exponentials, e to I k omega t. So you sum up over all k, and then you multiply these with slowly varying functions. So omega is larger than 1 over epsilon, so the exponentials here are highly oscillatory, but you modulate them with some coefficient functions, which are here denoted by zjk, and which change slowly. And then you can write down a system so that you can get an approximation to any order in epsilon of this type. But this is only a short-term approximation. But we want to use this approximation to obtain results over long times, and this becomes possible by observing that the equations that are satisfied by these modulation functions still has a Hamiltonian or Lagrangian structure with particular invariance properties. And if we have a Lagrangian, which is invariant under some continuous group actions, then we are in the realm of Noether's theorem, the theorem by Emmy Noether from 1918, so that's 100 years from now. And this Noether theorem is a prototypical example for combining geometry with dynamics. Noether theorem says that if you have a Lagrange function, which is invariant under continuous group action, then this implies a conserved quantity for the dynamical system. So from invariance under group action, you get conserved quantities. From a geometric property, you get a dynamical property. And it turns out that these invariants that you obtain from Noether's theorem for these extended systems just correspond to adiabatic invariants of the original systems. And in this way, Noether's theorem gives adiabatic invariants for such systems, and actually for a large class of systems which comprise continuous and both continuous and discrete, but weakly nonlinear oscillatory systems. And such weakly nonlinear systems to be considered over a long time, this is exactly the program that was laid out by in the last paper of Enrico Fermi, together with Pasta and Ulam from 1955. And let me just quote this. This report is intended to be the first one in a series dealing with the behavior of certain nonlinear physical systems where the nonlinearity is introduced as a perturbation to a primarily linear problem. And then the behavior of the systems is to be studied for times which are long compared to the characteristic periods of the corresponding linear problem. And this is exactly what these modulated Fourier expansions are good for. And they're good for it both in finite dimensional and infinite dimensional systems. And we now come to the infinite dimensional systems, where we take a viewpoint on Hamiltonian partial differential equations as such perturbed oscillator systems with infinitely many frequencies. So we can again use symplectic integrators for Hamiltonian partial differential equations and ask, what are the benefits? And just the simplest question, or seemingly simplest question, what can we say about the long time near conservation of energy? Now there are obstructions. The backward error analysis is no longer available for the interesting case where the CFL numbers are close to 1. So it doesn't work there. But even worse, for small CFL numbers, what you will get for a full discretization is then a preservation of the Hamilton function of the spatially discretized system, but it's not clear if this is related to the original Hamiltonian functions. So there are these obstructions. Nevertheless, you get good results in many cases, and I will just illustrate you one. Take the linear wave equation. This has particular solutions which are known as plane wave solutions. And you can ask, how do plane waves solutions, are they stable under adding a small nonlinearity to such a wave equation? And this question can then be reduced to a one-dimensional wave equation with periodic boundary conditions, where only the first Fourier mode is excited in the initial data. And this we have done here. And what I show you is, on the horizontal line is again the time axis, first on a rather short interval, then on a much longer interval. Initially, there's only a perturbation of the first pair of Fourier modes at with an amplitude of 10 to minus 4. And then immediately, the other Fourier modes are all excited, and they come up. So the second pair of Fourier modes comes up to the square, the third pair to the third power, and so on. But then the surprising thing is, although they go up immediately, they stay at this level. And they stay at this level for extremely long time. And so if we can prove such behavior, then yes, we have stability of plane waves under nonlinear perturbations, and we can even tell much more about the behavior of these curves and about the long-time preservation of the levels of the energies in the Fourier modes. So there are rigorous theorems which explain such pictures, and they are again proved using these modulated Fourier expansions. In joint work with Ludwig Aukler, who has done excellent work on a variety of problems in the numerics of Hamiltonian PDEs, again Ernst Heyrer and also Daniel Weiss. And this has been done both for the continuous problem and also for the numerical discretization. This is just one example. There are many more. I won't go into the detail, but they concern energy conservation in a weakly nonlinear regime over very long times. And the techniques that can be used here are again this modulated Fourier expansion. And there's another technique developed by Erwan Faou, which is a modified backward error analysis, modified in a very clever way. But there are also results about orbital stability for nonlinear Schrödinger equations, both for the ground state and for plane waves. Again, proved using modulated Fourier expansions or this modified backward error analysis. But now I would like to come to a seemingly, well, it's a different topic which will include different geometry, but which in the end will be combined with the Hamiltonian viewpoint in the last section. And this topic now is dynamical low-rank approximation. Now, what is this about? Generally, low-rank approximation is a very basic tool for data compression and model reduction. So we are considering the following situation, which is the simplest situation in this context that we can think of. We have huge time-dependent matrices, denote the A of t, so of dimension m by n, where m and n go into the millions or billions. Think of the adjacency matrix of an encyclopedia like Wikipedia, which changes in time. In that case, the matrices would be known explicitly, but there might also be the unknown solution of a matrix differential equation, say a discretization of a kinetic equation, like Vlasov-Poisson equation, or of a multiparticle Schrödinger equation. And now, these systems are just too big, so we want to reduce it to something more tractable. And we use a low-rank decomposition, which is like a truncated singular value decomposition. So I approximate A of t by a low-rank matrix of rank R, where this rank R should be much smaller than the dimensions of our matrix. And this is factorized into three components. This matrix U just consists of column vectors of a few long column vectors. Similarly, V of t, and S of t is a small matrix in between, which is invertible so that the rank is R. Now, such matrices of rank R form a manifold, which I denote here by M. So M is our low-rank manifold. And I denote by Py the orthogonal projection onto the tangent space at this at the point of this manifold. And then to approximate such time-dependent matrices to approximate such time-dependent matrices, I use this dynamic low-rank approximation, which just projects the vector field. So what we really want to solve is A dot equal f of y, and we just project the vector field onto the tangent space of the approximation manifold. So from a numerical analysis viewpoint, this is like a Galerkin method with a tangent space as the approximation space. But this is now solution dependent, state dependent. So we have a Galerkin method on the state dependent approximation space. It's a nonlinear Galerkin method. Quite surprisingly, this hasn't been studied in numerical analysis until about a decade ago. But it's well known in quantum physics, where already Dirac, 1930, proposed something like this in a particular example. And this is now known as the Dirac-Frankel time-dependent variational principle. Let me just give you a picture of what is done here. So here you see this curved manifold. You take a point on this manifold. You take the tangent plane on it, and the vector field would point out of the manifold, and you just project it to the tangent plane. And this is what is done here. And you might have noticed this is a barely hidden advertisement of a blue book. Okay. Now, to get a reasonable accuracy here is only available if the amount by which you project is rather small, which in our low-rank approximation would mean that we choose the rank sufficiently high, so that we truncate only small singular values, but then we cannot expect that the last retained singular value is large. This will also be small, typically. And this causes a problem because in the differential equations that you get for the factors u, s, and v, there appears the inverse of s. And this smallest non-zero singular value of S, this causes problems. And the problems that come here cannot be wiped away just by using, say, another representation. It's really a geometrical obstruction because the inverse of the smallest singular values corresponds to the curvature of the manifold at the point. And so we are in the situation where we want to approximate a manifold which has very high curvature. And then in the first moment, it doesn't look as if I could as if it would be a good idea to use such a tangent-based projection, because if you have, say, a crumpled piece of paper and you want to have an algorithm which just uses the tangent space, this doesn't look very promising. But this crumpled piece of paper is not a good model of our low-rank manifold. Here's a better model. This actually is a model from the 19th century in our mathematics department of a ruled surface. So you have a ruled surface, and in fact, our low-rank manifold has large subspaces, large flat subspaces. And this will save the situation here. Thanks to such a structure, we can get error estimates of this dynamic low-rank approximation, which are independent of the singular values, and then independent of the curvature. But now we also want to get good approximations which are independent of the small singular values in a completely time-discrete setting. And here we were lucky of devising such an integrator. So this is based on joint work with Ivan Osiledets, where we noted that this projection onto the tangent space can be given explicitly, and it is the sum of 3 subprojections. Now, splitting integrators have become very popular in the last decades in many fields, in the numerical, in many areas. And what we do here is just to split this projector into its 3 terms. And then we're lucky, because this gives us something which allows us to update our factorization in a cheap way, such that we solve differential equations only for these matrices which are composed of a very few long columns, and doing orthogonal decompositions on such matrices. There's no inverse of S as it would appear in the differential equations. And somewhat really surprisingly, this projector splitting integrator has amazing properties. First of all, it reproduces rank R matrices exactly. So that's a rare case that the numerical integrator gives an exact solution to differential equations, but here rank R matrices are reproduced exactly. And what's more relevant, typically you don't have rank R matrices, but you want to compute perturbations of such matrices. This admits error bounds, convergent error bounds, that are completely independent of the singular values. So the small singular values do no harm. Now, how is it possible to have such a robust algorithm? Now, the idea really is that this algorithm uses this ruled surface structure of our low-rank manifold. In each of the substeps of the splitting method, it only goes along flat subspaces. And in this way, it can, well, if you just go along flat subspaces, you can be blind to the curvature around. And that's somewhat intuitively what happens, but to make this, turn this into rigorous theorems, you need some more analysis, which I cannot present here. Well, so far this topic on dynamic low-rank approximation seems quite far apart from the rest of the talk, but the two come nicely together. The Hamiltonian viewpoint and this dynamic low-rank approximation come nicely together in the vast area of quantum dynamics. where one wants to compute numerical approximations. And then it turns out that these differential equations that you get from applying this dynamical low-rank approximation in a setting of now not matrices but tensors and tensor networks are still Hamiltonian partial differential equations. And you end up with Hamiltonian partial differential equations on low-rank tensor manifolds on which we want to do numerics. And if I would have been given a 2-hour talk, I would tell you much more about that. But now I think it's time to close, and I thank you for your attention.
Thank you very much for this very nice talk. I'm sorry that we don't have another hour. That is done for lunch. Unfortunately, we also don't do questions and question and answer session, but you can ask him over the break. I hope you stay for the break for lunch. Okay, let me thank you again.